Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 4, Lesson 9 on the inscribed circle and its center. Now today's topic is similar to one that we did in a previous lesson on the circumcircle and its center. So let's begin by talking about what the inscribed circle and its center are exactly. Now let's review what's known as points of concurrency. Recall that a point of concurrency occurs when three lines intersect at a common point. We have seen the circumcenter as a point of concurrency. In this lesson, we will see as another one known as the incenter. And to find it, we're going to use the following fact. Points along an angle bisector. All points that lie on the angle bisector of an angle are equidistant from the two sides, i.e. the rays, of that angle. All right. Now, this might seem obvious that like if you take an angle and you bisect it, right, with a line or a line segment or a ray, then every point that lies along that ray is equidistant from the two sides of the angle. But we should make sure we prove that before we use it. So let's take a look at exercise number 1. Given point D is on the angle bisector of angle BAC, DB is perpendicular to AB, and DC is perpendicular to ray AC, explain why BD, segment BD, must be the same length as segment CD, i.e. D is equidistant from ray AB and ray AC. So, side note, remember, whenever we're talking about the distance that a point is away from a line or a ray or a line segment, we're always talking about the length of a perpendicular segment from that point to the line, the ray, the segment, etc., right? So let's just kind of talk about, we'll get this down in words. Why does this point, have to be equidistant from this and this if it lies on the angle bisector? Well, think about this for a moment. If point D lies on the angle bisector of angle BAC, then what we know is that this particular angle, right, is equal to this particular angle, right? Now, we also know that that particular angle, which is a right angle, is equal to that particular angle, because they're both right angles. We also know, of course, that AD is congruent to itself. And therefore, triangle ABD is congruent to triangle ACD by the angle-angle-side congruency theorem, right? The angle-angle-side congruency theorem, and then because those two triangles are congruent, BD has to be congruent to CD by CPCTC because they are corresponding sides of congruent triangles. So let's get that argument down. We're just going to do it in paragraph form, okay? So I'm going to say, because AD bisects angle BAC, angle BAD is congruent to angle CAD. Also, angle ABD is congruent to angle, well, that doesn't look right, to angle ACD because they are both right angles. Finally, AD is congruent to AD. Of course, we call that the reflexive property. This lets us conclude that, go up a little bit, triangle ABD is congruent to triangle ACD by angle-angle-side. From this, BD must be congruent to CD by CPCTC. Yet again, CPCTC, corresponding parts of congruent triangles are congruent, rears its ugly head, right? But importantly, right, the takeaway from this The takeaway from this is that if a point lies on an angle bisector, then it must lie equidistant, right, from the two sides of the angle, keeping in mind that the distance then is defined as that length of that segment that is perpendicular to the particular sides of the angles. All right, we're going to now use this fact to help us find what is known as the incenter of a triangle. So let's get into that. The incenter and the incircle. Let me move that out of the way. We can use the fact that points along the angle bisector are equidistant from each side of the angle to find the incenter. Exercise number 2. For triangle ABC shown below, do the following. Letter A, construct the angle bisector of angle ACB. Fantastic. Let's review how to construct an angle bisector. First thing we're going to do is we're going to bring our compass up to here. We're going to put it on the vertex of the angle that we're trying to bisect, and then we're going to draw an arc with that center that intersects the two sides of the angle. Once we've done that, we then put the point of the compass, the center of the compass, at one of those two intersection points, and then maybe make that a bit larger. Try to keep that intersection point right there, and draw an arc, keeping the same radius that we just had. We put it then at the other intersection point and draw an arc, and that then forms the point that we can then draw our angle bisector through. And that line then bisects angle ACB. Fantastic. And keep in mind, right, that every point along that line segment, or along that line or ray, lies equidistant from side AC and from side BC. Now let's take a look at letter B. Construct the angle bisector of angle ABC. All right. Well, again, this construction is basically so important for what we're doing today. Let's do that one again together. So now I want to bisect angle ABC. So I'm going to, again, put the tip of my compass at point B. I really want to try to do this as accurately as possible, or my incenter will be off. So I make that arc, come over here, maybe make this a little bit longer, and draw an arc there. These pictures can get very complicated. Draw another arc there. I'm going to just mark that intersection point. It's right there. Easy to kind of forget what we're finding the intersection of here. And now let's draw in that angle bisector. I think I need to rotate it just a bit more. Ah, that looks good. Okay. So we've got our 2 of our 3 angle bisectors, right? And letter C, mark the intersection point of the lines you drew in A and B as point D. All right. Now, no great surprise, that will be our incenter, but we want to show that it's a point of concurrency. Let's talk about this, right? Take a look at letter D. Explain what special point D is compared to the sides of triangle ABC. Well, again, think about this for a moment, right? Point D, because it lies on the first line that we drew, must be equidistant from side AC and side BC. Now, point D also lies on the second line that we drew, which means it must lie equidistant from side BC and side AB. Well, if it lies equidistant from AC and BC and equidistant from BC and AB, then it must also lie equidistant from AC and AB. So point D is the point that lies equidistant from the 3 sides of the triangle. Now think about this compared to something that we saw in a previous lesson called the circumcenter. That point lied equidistant from the 3 vertices of the triangle. This point is going to lie equidistant from the 3 sides of the triangle, all right? So point D is equidistant from the three sides of the triangle. Now, again, make sure you kind of understand what that even means. If I went from point D perpendicular to BC, I'd get a particular distance. If I went from point D, let me get that final vertex in there. If I went from point D perpendicular to side AC, I'd get another distance, and those two distances would be the same. And finally, if I went from point D to point AB, right, perpendicular, then that distance would be the same as those other two, right? So point D is the one point that is the same distance away from all three sides of the triangle. Now, let's take a look at letter E. Construct the angle bisector of angle BAC. Verify that it passes through point D. All right, well, this one is the moment of truth, right? If I've done a good job locating that particular point, then the third angle bisector should also pass through it. So let's see how accurate my incenter is. All right, always makes me a little bit nervous, but let's see. All right, I'm going to put my tip of my compass at A. Draw an arc. Of course, that tip of the compass didn't stay at A, but fine. This is where the inaccuracies come in. All right, so I want to do the bisector. Really want to get that tip at that intersection point. All right. Good. Oh, I didn't want to do that. I do not want to change the length of that radius, and of course, now I'm not going to get it back, but hopefully that's close enough. All right, let's see. I already know that I've got some inaccuracies here, but hopefully they won't be fatal. Let's bring it up here, and let's see. Oh, that's not actually too bad, right? When I draw that angle bisector in, it pretty much goes right through D. Woo. All right. So the three angle bisectors of any triangle intersect at what's called the incenter of the triangle and are a point of concurrency. Now, again, think about this, right? That point lies equidistant from the three sides. And just like the circumcenter, we have a circle then that will have this as its center. The question is, what's the radius? Well, let's take a look at letter F. Construct a line segment that passes through point D and is perpendicular to BC. Okay, so here's actually a new, right? Not a new, but it's a different construction than what we were just doing. I want to construct a line, and we've done this quite a few times. I want to construct a line that passes through D, but is perpendicular to BC. And I could do the same thing except perpendicular to AB or AC, but BC is going to be the easiest one. So remember how we do that, right? We bring our compass over, we put its tip at B. All right, we extend the compass far enough so that if I draw an arc, it will pass through BC twice. I always like to kind of take a look and see if that will actually happen. And I've got it. Right, now what I'm going to do is I'm going to move my compass down so that its center is at one of those intersection points. Maybe widen it a little bit. All right, like that. And then put the tip here as well. Come on. There we go. That should be, there's my ruler. I'm like, where'd my ruler go? I put it somewhere. Let's see. Rotate my ruler down. X marks the spot. That is now a line going through D perpendicular to BC. Now, why did I do that, by the way? Well, the reason I did that is I wanted to get the radius of the circle. I wanted the distance that D was away from BC, and that's this distance, And that's the final little piece, letter G. Using point D as the center and the segment you drew in F as a radius, draw the incircle, or the inscribed circle for ABC. This circle should be tangent to the sides of the triangle. In other words, just touch them. All right, so let's do it. Again, moment of truth. How good is my incenter? The fact that the three angle bisectors actually all coincided there was great. All right, I don't know if I'm going to be able to get this perfect, but I'll get it as good as I can. All right, here we go. Oh. All right, well, that's not great. All right, so that circle, if it was really, really perfectly drawn, all right, would hit the circle, would hit the triangle, just graze the triangle here, here, and then this should be like right here. Anyway, it's tough. It's tough to get the incircle perfectly, but the incircle should all be within the triangle, all right, and it should touch the three sides of the triangle in just one place, all right? It should be tangent, right? And really, it should be touching the triangle at the three locations that would then be perpendicular to the sides from the incenter itself, all right? And again, it's that way because those three perpendicular distances should be the same. And again, here and here, they're pretty good, but here, not so much. All right, so let's talk a little bit about this. Whoops, there we go. Location of the incenter, right? Unlike the circumcenter, the incenter of a triangle will always lie inside the triangle since the incircle must lie inside of it as well, all right? But like the circumcenter, we don't have to draw all three of the angle bisectors, we just really have to draw two of them. Because it's a point of concurrency, all three angle bisectors will intersect at the same point, so there's no reason to really draw more than two of them. Let's take a look at exercise number 3. For obtuse triangle LMN shown below, do the following. Letter A, construct the incenter for this triangle, mark it as point C. All right, so unlike the circumcenter, which once you have the circumcenter, it's really quite easy to draw the circumcircle. The incenter and the incircle are kind of two beasts all in and of themselves. So let's first find the incenter by picking any two of the vertices and creating the angle bisectors. I'm going to start with angle N and then do angle L, but let's do angle N together and then have you do angle L on your own, or you could do angle M, it doesn't matter. But I'm going to do angle N first. I'm going to find its angle bisector. So let me just scroll my screen up a little bit here. Let me put my tip of my compass there. Widen the compass out a little bit, get an arc, right? That's always my first step. Then I want to get that arc, draw two more arcs. Oh, I'm going to go a little bit bigger maybe. That looks good. Leave my radius the same, bring the center so that it's at the other intersection point. All right. X marks the spot. Let's bring our straight edge over and draw a line through vertex N and where those two rays, or those two arcs intersect, and that should be the angle bisector of angle N. All right. What I'd like you to do is find the angle bisector, construct the angle bisector either for L or for M, shouldn't make any difference, and the intersection of that particular angle bisector with this one, we're going to want to label as point C. Pause the video now, and again, as I said, I'm going to do point L if you want to do the same thing I do. All right, let's do it. So first things first, let me get the tip of my compass right at L. All All right, open it up again. Let me try to get it actually at L. All right, got myself an arc there. Now we'll use that, come out here, maybe make it a bit bigger. All right, make this arc, bring it over here, make that arc. There, we've got our intersection. I love the angle bisector construction. It's very simple, it's very neat, it's very easy. The only issue is that I've got to do two of them. I feel like that should, there we go. Okay. If I've done my job, that should be the incenter. All right. So finding the incenter is quite simple, right? Do the angle bisector construction on two of the three angles of a triangle and find the intersection point of those two. It will always be inside of the triangle. It doesn't matter whether the triangle's acute, obtuse, or a right triangle, always inside. Now let's take a look at letter B. Construct the incircle for triangle LMN. Now, to construct the incircle, what we always have to now do is we need to construct a perpendicular line that passes through the incenter and is perpendicular to any one of the three sides. It doesn't matter which, okay? For me, I think I'm going to draw it perpendicular to side LM. LM is nice and large, no big deal, right? Should be simple enough. So let's draw a line that is perpendicular to LM and passes through C. Now again, remember to do that. The first thing I have to do is draw a line through LM. Sorry, just making sure that it's correct. An arc through LM centered at C that intersects LM twice. There we go. Right, now I come up here and I use that to draw two more arcs. Oh man, my pencil must be getting dull. There it is. Oy, okay. Now let's bring it over to here. I really want this to be accurate. I want to get a better incircle than I did last time for you. Great, let's move this over here. You've still got a little bit more work to do. All right, so now, whoops, can't lose that intersection. Now I just need to draw a line that goes through my incenter and that intersection point. Again, the whole idea here, the whole idea with that is we're trying to figure out this particular distance. Let me, oh, I lost my pen icon. Anyway, we're just trying to figure out that distance. That's all we want, right? Because that's going to be the radius of our incircle. Okay? So now to draw the incircle, we bring our compass back down to our incenter. And we're going to expand it until it is the length that we have right there. That looks great. Moment of truth. Come on. Not bad. Not bad at all. There we go. Much better than the last one, right? A circle with the center at C that is tangent here, here, and roughly there, right? Not that it asked you to circle the points of tangent C, but I did so anyway. All right, anyhow, so two pieces, right, to this incenter idea. You know, one piece is just simply the angle bisectors, drawing two of them, constructing two of them, finding their intersection point. There's our incenter. Then having to draw a perpendicular from that point to one of the three sides of the triangle to establish the radius of our incircle. Lots of ins here. All right, let's take a look at one last problem. Exercise number 4. In the diagram below of isosceles triangle QRS, segment QS is congruent to segment QR. The altitude from Q to RS has been drawn with point T on RS. Letter A. Explain why both the circumcenter and the incenter of this triangle must lie on QT. All right, now, if you didn't watch our lesson on the circumcenter and circumcircle of a triangle, then this isn't going to make a lot of sense, or if your teacher didn't already do the circumcenter and the circumcircle. All right, but remember, the circumcenter is located at the intersection point of all the perpendicular bisectors of sides of the triangle. And the incenter is located at the intersection point of all the angle bisectors. So why does the circumcenter and the incenter have to lie on this altitude? Well, it's pretty simple. The altitude of an isosceles triangle from the vertex to the base is also the angle bisector, and it's also the perpendicular bisector of the base. So, right, QT is both the perpendicular bisector of SR and the angle bisector of angle SQR. All right. So those two things, right, the angle bisector and the perpendicular bisector of the opposite side, those are rarely the same line. But they always are when you're talking about an isosceles triangle and you're drawing the altitude from the vertex angle to the base of the isosceles triangle. So it's cool. Both the circumcenter, right, the center of the circle that goes around the triangle, and the incenter, the circle that is inside of the triangle and tangent to its three sides, that point, or those 2 points, sorry, must lie on QT. Okay. Let's take a look at letter B. Construct the incenter of this triangle, label it point I, draw the incircle. Awesome. Well, since we already know it's on QT, we just need to do the angle bisector of either angle S or angle R. I'm going to do it for angle S. Let's do this together. So let's do the angle bisector of angle S. Now I'm going to bring my compass over. I'm sure you're getting very tired of this particular construction given how many times we've done it in this lesson, right? I draw an arc centered at S, bring now my compass over to one of those two intersection points. Okay, I'm gonna draw this arc. I'm gonna try to draw this arc. There it is. I don't understand why sometimes it does not draw the arcs, but that is the mystery of technology. There we go. I can now draw my angle bisector, maybe make my ruler a little bit smaller. And let's take a look. Okay, that's actually pretty good. There it is. Since we now have two angle bisectors, right, where they intersect has got to be the incenter. We could draw the third one, but it would go right through I as well. Now, it also asks us to draw the incircle. Now, typically at this point, I'd have to take this point, the incenter, and I'd have to construct a perpendicular line from the incenter to one of the three sides. But the cool thing is I already have it. It's right here. I don't need to draw that again or construct that again like I did in the last two exercises because I already have it. In fact, all I have to do now is put my compass right there at the incenter, and I need to just measure out how long that is. Okay, so I want to try to again get this as accurate as possible. That looks pretty good. Come on, circumcircle, or come on, incircle. This is not the circumcircle, it's the incircle. And it's not too bad. You know, for me, that's quite good. Again, it, you know, definitely tangent here, looks pretty good there. Not quite there, but you know, that's pretty close, right? So we've got our incenter and our incircle. Let's review a little bit about the circumcenter. Let's take a look at letter C. Construct the circumcenter of this triangle, label it point C, draw the circumcircle. All right. Well, again, the circumcenter will be at the intersection point of any two of the perpendicular bisectors of the sides of a triangle, and we already have one of them. So we simply have to construct the perpendicular bisector of one of those two legs, I think I'll do the perpendicular bisector of, maybe I'll do the perpendicular bisector of QR, all right? I think that'll work. Maybe. Actually, maybe I'll do QS just to try to keep my poor compass on the screen. So we'll just construct the perpendicular bisector of QS, right? Just have to put the point at S of the compass and then get an arc that is more than half the length. I'm going to have to go through some of the text here. I apologize. All right, then we'll move it down here and get another arc. This is going to get awfully messy, but that's okay. Switch, put the point up here, right on Q, like that. Bring it back down, find that other intersection. There it is. Bye-bye for now. Bring this up, and now let's get that perpendicular bisector. And that looks good. All right, and notice they're in different places, right? That's supposed to be point C, right? So I've got my perpendicular bisector here of SR, my perpendicular bisector here of SQ. Where they intersect, okay, is going to be point C. I think I'm going to move this I. Whoops, that didn't help. Anyway. We'll leave I where it is considering it's attached to that. Now I have to draw the circumcircle, right? It's going to have a center at C, and it's going to have a radius from C to any one of the three vertices of the triangle. All right, so we're close. It's probably as good as I'm going to get. Oh, man, just a little bit off there with Q. Pretty close, right? In theory, had I located the circumcenter perfectly, then when I drew a circle around, it should have intersected point S, point R, and point Q perfectly. It was just a little bit off on point Q, but pretty close. And again, notice, right, that the circumcenter and the incenter are different points in this case. Right? And that kind of makes sense because if you remember our lesson on the circumcenter could be inside the triangle, it could be outside the triangle. If we were talking about a right triangle, it was at the midpoint of the hypotenuse. On the other hand, the incenter, because it's the center of a circle that has to lie inside of the triangle, the incenter also has to lie inside of the triangle. So they don't have to be the same point. But let's take a look at exercise number 5. Clearly, the circumcenter and incenter of the triangle above are not the same point. Do you think there are any types of triangles for which they are the same point? If so, what types? All right, pause the video now. I bet many of you can figure this out. What types of triangles will the incenter and the circumcenter be located in exactly the same place? Well, if you said equilateral, you are correct. All right, so in other words, right? A triangle that has all three sides the same length, right, will then have an incircle and a circumcircle that has a point that has the same center point. And it kind of makes sense because in this case, what happens is that the three angle bisectors also happen to be the three perpendicular bisectors. They are literally the same lines, and therefore their point of concurrency is the same point. And it's kind of cool, right? I mean, you can really see it with equilateral triangles. All right, let's wrap this one up. So today we saw a second type of point of concurrency called the incenter. And the incenter is located where the three angle bisectors of a triangle all intersect. That intersection point gives rise to a very special circle known as the incircle or the inscribed circle, all right? And the inscribed circle is simply a circle, right, that is tangent to all three sides of the triangle and always lies inside of the triangle, all right? And it's kind of a beast to construct because the first thing you have to do is find its center by finding the intersection of two of the three angle bisectors. But then you also have to draw a perpendicular line from the incenter to one of the three sides to simply determine what the radius of the incircle is. All right, so it's a little bit tricky, a little bit complicated, and as you saw plenty of times here up on the board, kind of hard to do very accurately without really good computer software, and I'm not talking about the kind that I have, all right? Anyhow, I want to just thank you for joining me again for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.